what we want to do. We kind of know this is true already. You've seen it in calculus or maybe sometime. But I want to actually prove that this is also true, that for partial derivatives, it doesn't matter what order you take the derivative in. That seems a little bit less likely to me because based on what we just looked at, it certainly seems, because you sort of kill a bunch of things when you take a derivative with respect to time and like assume that this is constant. You sort of kill a lot of things because you're assuming a bunch of stuff is constant. So it's not totally convincing to me that this commutativity thing actually works, that the order doesn't matter here. But it actually does. It's actually true. So I'm going to show it. It's pretty easy, actually. So first, we just have to remember what the definition of derivative is using limits from calculus. So that's the rigorous definition of derivative from your calculus class. The derivative of x is a limit, as this small parameter epsilon goes to 0, of the difference of f evaluated a little bit further than from the x place you actually want to evaluate it at, a little bit further subtracted by the original divided by epsilon. So you can think of that as like, okay, here's your f, here's your x. You're going to like evaluate f a little higher up here. You're going to find what that is. Then you're going to subtract off this guy, and you're going to divide by epsilon. But you're going to do that as epsilon gets smaller and smaller. That's the literal definition of the derivative, and that's how you get the slope being right there. So that's the literal definition here. So what I'm going to do is give you the literal definition for the partial derivative and then show you that this commutativity still works. So fortunately, like many things in math, it's just as simple as it could possibly be. If I'm going to take a partial derivative of something which is two variables, with respect to one of the variables, I just do this limit thing in only one of the variables, only the variable that I'm evaluating this as. So that's going to look pretty simple. So notice I took the limit as epsilon goes to 0. I've only advanced the x part of the function, not the y part of the function, right? This is x plus epsilon minus f of x, but I've kept the y exactly the same. So the y is not changing when I take this derivative. That's what the partial means, right? Is I only take the derivative, I only check to see how the function changes as I go along one of the two directions. Okay, so this is going to be our basis for wanting to prove that it doesn't matter what order we do the two derivatives in. And the first thing I'm going to do is I'm going to take the second derivative of this guy. I'm going to take the derivative with respect to y, because that's going to give me the second derivative, x first, then y. And then I'm going to do the opposite. I'm going to take dx dy, and then we're going to see that they're actually going to be the same. So that's what I want to evaluate. That's just rewriting, so the y pulled out a little bit, but that's because I have this written down here already. So now I'm going to replace this into right there. Okay, and now I have to do the same thing to apply the partial derivative, meaning here I had to advance the x variable by epsilon and then subtract out the original. So I need to do the same thing here, except with this entire expression. So I need to have first this thing evaluated at epsilon a little bit bigger of y, and then subtract off this thing evaluated at the original y. So that's going to look messy, but it's pretty simple. I'm just applying the derivative, meaning I'm going to have a new epsilon, something like epsilon prime, which is just going to apply to the y variable and subtract off this entire thing exactly the way it is, the same way that it's exactly there, the same way that the original function was. Okay, so that's this thing with the y evaluated at y plus epsilon. Now I'm going to subtract off exactly this thing, that is y without the plus epsilon. That's there. Now, of course, the definition of the derivative is that you take the limit of epsilon prime goes to 0. There's epsilon prime right there. But then you divide by the entire epsilon. So I have to divide this entire thing by the new epsilon prime. Okay, so obviously that looks a little bit ugly. I'm going to rewrite it one more step before going on to doing the opposite one, the x, y one. The way I'm going to do that is I'm just going to notice that these guys are all on the bottom. So epsilon so 1 over epsilon divided by epsilon prime, that's 1 over epsilon times epsilon prime, right? This guy goes on the bottom, can go on the bottom here and here, so that's going to make it simpler. And also, I'm going to notice that the limit, it doesn't matter that the limit is applied to each one individually. I can just pull the entire limit out, right? Because if I apply epsilon to 0 here and apply epsilon to 0 here, it doesn't matter how I put that instruction. So I'm just going to put that all the way at the beginning and rewrite this entire expression. Okay, there we go. Looks ugly, but it's relatively well understandable because we know what the limits are, we know what the primes mean, all that kind of stuff. Be a little careful, this minus sign applies to this whole thing. I should maybe put parentheses around there, whatever. Okay, so now let me try the opposite one, x first, then y. So first split it into 2, just like I did here. Now apply the first limit, meaning just put in the regular definition of the partial derivative, but now the limit, the changing variable applied to y instead of applied to x. Okay, so you can see that I advanced just the y variable by epsilon. Okay, and now I'm going to have to do the same double application I had to do before to do this partial derivative. So I want to advance the x by some other small increment epsilon prime, and then subtract off this thing without the epsilon prime. So there's the first one, advancing x plus epsilon. There's the second one, which is exactly this without the epsilon prime in it. And of course, I haven't divided by epsilon prime, so I've got to divide the entire thing by epsilon prime. Good. And now to make a comparison with the line up here, I again want to simplify the expression by pulling out the limits and putting just the epsilon on the bottom. So this epsilon divided by epsilon prime will all be 1 over epsilon times epsilon prime in the same way that it is up here. Okay, so sorry the board is so covered, but we are basically done. So we want to look at this line right here and this line and decide if they're the same. Now, the first thing we can notice over here, the limits are the same, good. We can look, but if we look inside the functions, we can see the epsilons are actually in the wrong places. So this is x plus epsilon, this is x plus epsilon prime. This is y plus epsilon prime, y plus epsilon. Same thing, they're very, very close. In fact, this one is over here, x plus epsilon y, x plus epsilon prime y. So they are jumbled a little bit, x, y plus epsilon prime, y plus epsilon, and then they're the same here. So they're jumbled a little bit, but they're the same up to the changes in epsilon and epsilon prime, right? So if this thing said just epsilon, that term would be right there, even with the correct minus sign, right? So the minus signs are also totally right. And if we just want to be real careful about that, the one with double epsilon is positive. The ones with single epsilons are both just with one negative sign on them. And then the ones with no epsilons have a positive sign. So yeah, they're the same. Okay, so here's what we're going to do. We're just going to relabel them, right? Because the epsilon doesn't matter. It doesn't matter what we call those two epsilons. I could call this epsilon prime banana and call that epsilon prime star or something. So all we can do is if we just relabel all of the epsilon primes to epsilons, they'll actually be the same. So let me do that by taking this one and erasing the epsilon, the primes, and just replacing the other ones, just adding the primes on the other one. Okay, but since I've done that, now they're exactly the same. That is epsilon, epsilon prime. The one with one minus sign is epsilon prime, x plus epsilon y, right there with a minus sign. Positive sign, no epsilons. The denominators are switched, but of course those are just multiplications, so a times b is b times a, so there's no problem if those two are switched. These guys are switched, but taking limits is commutative, so it doesn't matter what direction you take limits in, you'll always get the same answer, and so therefore these are exactly the same expression. So we've just proven that this order of taking the derivatives with y first and then x is the same as this order of taking derivatives, x first and then y, just like for regular derivatives. Okay, great. So that was a bit much, but I do like this kind of like rigorous analysis of mathematics to make sure that we all know what we're doing. And we should always remember what the definition of the derivative is, even though we use it as dropping powers and changing sines and cosines and things like that. But this is the real definition of the derivative. Everything we do goes back to here. And it's just good to prove to ourselves that these simple things that we know about derivatives and now partial derivatives are actually totally true. Not that hard to like prove that they're true. Okay, great. Hope this has been helpful, and I will see you in class.